In class, we learned how to investigate relationships between numeric variables visually using scatterplots and a little bit more quantitatively using correlation coefficients and regression equations. Today's lab will focus on using technology as an aid in this pursuit. So we have before us the Students 15 data set from a spring 2015 survey of Math 37 students. And what we're going to do is look at how much a student paid on their last haircut, which is the variable hair.cut, depends on their risk score. So as a first step, we're going to create a visual scatter plot. And creating a scatter plot in R has the form plot x comma y, where x is your predictor and y is your response variable. So since we'd like to see how haircut price depends on risk score, we're going to choose risk score as 15 as our predictor. And we're going to choose haircut as our response. So if we simply create a plot like this, we see a scatter plot that shows that there's probably very little correlation between these two variables, although we also note that there's a large number of outliers here which could be affecting the analysis. Now, just to remind you from the previous lab, if you'd like to change the labels on the axes, you can add the command xlab and enter whatever string you'd like to label the x-axis with. So if we wanted it to be risk score, and you could do a similar sort of thing for the y-axis, and there are other options you can enter in plot, like changing what type of markers to use at the different points and whatnot. So if we actually want to quantify the relationship, the strength of the relationship between two variables, we can compute the correlation coefficient, which in R is just the command core. Right. Students 15 $hair.cut. And we can see that there is a slight negative correlation, but really almost no correlation between these two variables. Now, if we want to remove these outliers, or if you want to remove observations in general because you think they're bogus, or you just want to investigate a question that doesn't involve that subset of the population, in R, it's very easy to create new data sets which allow you to do that. So let's say, for example, that we want to create a new data set, which I'm just going to call S15, which takes the previous one, okay, but is going to remove all of these outliers who paid more than $150 for their last haircut. Right. In that case, then, we enter the name of our data set, and then in close brackets, we're going to enter a condition, okay, so $hair.cut less than 150. And what this is going to do is this is going to say only include the rows of this data set with this condition. And then this comma here with a blank next to it says to include all of the columns of the data set in the new S15 variable. So now you should have a new variable in your workspace called S15. And there were 5 observations removed. You can see this by comparing the length. And if you view S15, you can see that it does indeed have all the variables before, but again, those 5 individuals were removed. So now, if we'd like to look at how this changes the picture, we can go back to our plots, and we can replot our data, and we can see that it still doesn't really look like there's much correlation between the two, and that's okay. So the final thing we wanted to demonstrate in this lab is how to actually compute the equation of the regression line in RStudio. And this can be done using the lm command. ln stands for linear model, and it's a very powerful function in R, which we'll investigate further later in the semester. The syntax for the lm command is similar to the box plot syntax from the last lab, where you have to enter one variable as your response, so in this case, hair.cut, followed by a tilde, followed by your other variable. And then we want to specify what data set to use. In this case, data equals S15. And you can see then that the lm command will spit out both the intercept and the coefficient of our linear model or regression equation.